Thank you. The problem is whether P is equal to NP. And it's that problem I'm going to talk about. And then I will relate it to AI and theorem proving and see what computers can do about it. So first I try to go through the problem. An outline of my presentation is, first, I will deal with the Hilbert proof theory. And Hilbert proof theory is what I'm using. And what I'm going to use of that is that I'm going to give an axiom for Turing's theory of computing. And then from this axiom, I will present informal proofs. But the requirement of the proofs is that it should be possible to transform them into, for example, a proof in predicate calculus. And if that's not possible, it doesn't belong to Hilbert's proof theory. And why is it interesting to have the proof in predicate calculus? Well, that's one of the systems that theorem provers in AI are used to work with. But obviously, you can do it other ways too, but that's a convenient way at the moment for theorem provers. Turing defined computing 1930s. And that is essentially what we understand today as computing. So I'm going to give an axiom for that theory. And that axiom is called B. And it is a universal Turing machine. And that's a brilliant idea that Alan Turing had. I'm not going to go into the details, but I'm going to look at the axiom and show some of its properties. And then I'm going to talk about complexity measures. You can measure the complexity of a problem in several ways, and I'm going to take up two. And then a few corollaries that follow rather straightforward. Then, the main result, that is lemma 1. And that follows from the axiom, of course. But it's the axiom that is important to give lemma 1. And I will show a proof. And then we will see how lemma 1 and an earlier theorem from mid-80s, Haken theorem, is useful. If you put these two together, we will get theorem 1. That SAT is not in P. And SAT is the problem of deciding whether a propositional formula is satisfiable. Is it possible to make it true or not? And the SAT problem is in NP. You can write a non-deterministic Turing machine that in polynomial computing time decides if propositional formula is satisfiable. If SAT is not in P, then P and NP cannot be the same SAT, of course. So P is not equal to NP. So that's a general outline. And then when we have seen how this proof of lemma 1 goes, we can ask ourselves, what can computers do about this? So first is this Turing theory. And I have axiomatized it. And the two first sentences here, that's to define this T predicate, because it's more convenient to have only 3 arguments instead of the U one that is much bigger. I come to the U later. So what this is, the first argument of the T is a Turing machine, and that is a sequence of quintuples. Could be long. So here is the input. A is the input, here is the Turing machine, and here is the output that it computes. That's the idea. And the T predicate is convenient. So here I just define that. And then we come to the real universal Turing machine. So the universal Turing machine gets a particular Turing machine, and it works as the particular Turing machine would have done the work. So from this sequence of quintuples, it just has a tape, and you measure the complexity by counting the number of times the head moves on the tape. There is a tape, a Turing machine. It has a tape that it works on, and it has squares, and it has a head. So it reads here, and it moves one square to the left, one to the right. And each time it moves its head, that's a measure on the complexity. Okay, so without going into some details, this first statement is a halt statement. So when the machine comes to this state, the 0 state, it stops. Then it has an output. So what it has here on the left part of the tape, that becomes the output. So this is kind of a logic program, if you like. So here is the tape, the left part, and what is on the tape becomes the output. And you stop computing. And this one is a move to the left. The 0 means that the head here moves to the left, and it writes something, and it reads what is on the tape. That's this statement. And this one is a move to the right. And here is when it is looking up a quintuple. The Turing machine has a sequence of states and a symbol. And it is in a state, and it reads a symbol. And then it looks up after a quintuple here, what to do. If it doesn't find a quintuple, it fails. So in order to go on, it has to find a state and symbol to go on working. But that doesn't count in the complexity. It's inner work. And that is what happens here in this statement. Here it searches for a quintuple from which it can start working. Okay, so this is a universal Turing machine. And its simplicity, why it's useful, is that it is in every statement here only 2 predicates, and here's just 1. And that computes special type of proofs, because everything we are going to prove here in Hilbert's proof theory is proofs in Robinson resolution. It doesn't have to be resolution, but that's what we are after, because Haken has a result about Robinson resolution proofs. So we will use this axiom to compute results about resolution proofs. And resolution proofs is what you use usually in logic programs. Prolog, for example, uses that. Okay. So this idea of quintuples is a very precise description about what an algorithm is. Sometimes you say, I have a good algorithm. And usually that's good to have a rather informal description to solve a problem, what an algorithm is. But in this case, we are using that an algorithm actually is a Turing machine, a long sequence of quintuples. And that's all that is given. Okay. So what we need here are a few measures of complexity, the complexity of a problem. So one measure I have already mentioned, that is to measure the computing time, is it called, which is the number of moves of the head of the Turing machine. And that was Hartmanis and Stearns that came up with this idea. It's a bit different here. I have only one type. They had several types. But that doesn't change anything with respect to this problem anyway. And of course, it's simply just to have one type. And another way of measuring the complexity of a problem is to measure the size of a proof. So if you have an axiom and you prove something, you can measure how many symbols are involved in that proof. That's one other way. And that is when we are looking at the resolution proof, we're going to look at how many symbols are involved in this proof. So there are 2 different measures of complexity that we are going to use. And in this theory then, the computing time is the number of moves of the head of a Turing machine in a formal deduction. Okay. So then I need a notation. I'm going to use that. This notation here, it stands for there exists a proof from axiom B of this formula in Z. And the Z is in how many times I have moved the head of the Turing machine. This is an informal expression, but it's convenient to have it. And it's possible to transform it into predicate calculus. OK, so now we take up the problem of satisfiability. If you have a propositional formula, to see if they can be made true, if they are satisfiable or not. So I start here with a set, it's non-empty, of deterministic Turing machines that compute whether G, that is a proposition, is satisfiable. If it is satisfiable, it writes an output of 0. If it's not satisfiable, it computes another output, which is 1. And it does that for all propositions. And there are machines that do that. So we assume, for the sake of our argument, we make a big assumption here. We assume that there is a deterministic Turing machine, and we call it I. And the kind of work it does, it takes a propositional formula as input, and it computes the output. And it does that in polynomial computing time. That means we take the size of this formula, and it must be possible to express it as a polynomial. So that's the measure of what this machine does. And we call this machine I. I'm not using this deterministic Turing machine in any other way. But that's the assumption about it. We are not sure that there exists such a machine. So we will see what the argument will lead us. Then, definition of I. So we define this as if not G, propositional formula G, if that one is not valid, then it's satisfiable. Then we give the output 0. And if the not G is valid, that means valid, then the G is not satisfiable. And it writes the output 1. And then we get a useful result, but it's rather trivial. This Turing machine I can use that. And if we run it, so if we have I applied on a negated F, and it says unsatisfiable of the negation, then F is always true. And then we define sat is in P. If sat is in P, then that means that if we try to prove that this negated formula F, that is a tautology, and if I then says the negation of F is unsatisfiable, then F is a tautology. And computes in polynomial computing time. So that's the definition of in this Hilbert proof theory, and that is useful to have. Okay. So we can from corollary 1 and definition 3, we get a corollary 2 here. So if sat is in P, then we can, for all tautologies F from B, we can find a proof in polynomial computing time. Then I will introduce another notation. R stands for Robinson resolution. And this proof that exists of F, we measure its size. And the size is polynomial. This is a convenient way of saying that the size of this proof is polynomial in the size of F. Okay. Now we come to the essential first result here. And that says, if sat is in P, then there is a size of a resolution proof of F that is polynomial size for all sufficiently large tautologies F on DNF. All of a sudden, we are only talking about all sufficiently large. Well, because Turing machine I that we have been assuming that exists when we compute our proof here. That is from the axiom, and that is I apart. So the formulas of the axiom become big. So we are first given I, and after that, which could be huge, we can choose f's such that the size of the resolution proofs do not depend on I, it only depends on f, because we can always, these tautologies can be arbitrarily large, so we can always choose a really, really large one. So the measure of the proof is not dependent on this I that we have assumed exists. So this is why we are not talking about all tautologies, we are just talking about the sufficiently large ones. Okay. So let's assume that SAT is in P. And from the definitions we have given, by corollary 2, we get this one. That says that, well, if SAT is in P, then we can prove F from axiom B in polynomial computing time for all tautologies F on DNF. Okay, so in logic programming terms, that would be like we have this program B and we want to prove F. And we are measuring how many times B is using its head. And it's not allowed to move more than polynomial many times with respect to F. And when we have that, we have done that in a resolution proof. And then we can measure this resolution proof. So that's what we are going to do. So this is how it will look. So if you start here with B and F, and we start out with the axiom is in first order logic, so it's not propositional formulas. But while we are computing here, we are computing propositional formulas. An instance of the B is this propositional formula, and we have that goal. And then we get, by solving this goal, we get that goal. And here we compute another instance of the B. And here we move on, and here is just against the ones we are doing the resolution. I present this in a clean G4 system. That's just because it's convenient to present resolution proofs in this system. But I could have presented it in resolution itself, like you do when you do prolog computation, for example. So now we start out the computation here. And from the axiom, we know what's happening. These U's are the short versions of the bigger U's, if you remember in the axiom. There was a U's predicate, but that would be too big to write here. So I've shortened it down. And I have given indexes here also. And that's just make it simpler to measure the proof. So the first index is the computing time. The head moves. So it moves up here. It has to be polynomial in the size of F. So up here it stops, and it finds a solution, because that's what we have assumed. SAT is in P, so it will find its solution in polynomial computing time. And then the second index is the number of formulas that is needed in the computation to find a quintuple, so it can continue its computation. We get the resolution proof here. And now it just remains to measure how big is this proof. How big is it? If we take the other measure of complexity to measure the resolution proof. And that is essentially everything. And it's not difficult to measure. This doesn't go on more than in polynomial computing time. And the formulas here that are involved, they are never bigger than polynomial size. It never searches more than polynomially many quintuples. So we can conclude that the size of this whole tree is never more than polynomial. Informally, that's the result. For sufficiently large F. That works for the sufficiently large F's, because otherwise these formulas could go on here when it searches for a formula in the I, because the I could be huge. So that would give not such a good information of how complex the problem is relative to the input F. So if you take big enough F's, we have a proof here in resolution that we can measure. And it goes on only in polynomial computing time, and the new formula is bigger than polynomial size. So the whole tree is just polynomial size. Okay. When we go up here in the proof, we are computing the propositional formulas. Not doing anything but instantiating the formulas, making them propositional. We are not changing the structure. We are not redefining anything. So when we are up here and we have been computing in polynomial computing time, we can just collect the propositional formulas that we have got. Then, if you remember the blue ones, here they are again. So if you see here, here's one formula and here is that one implies that one. That's an atom. So it's very simple structure of the proof that we collect of the propositional formulas. And why is it simple? Well, that's the simplicity of the axiom. It has this form. So the only thing we have done, we have from first order formulas, propositional formulas. That's all, nothing else, no other transformation. And now we can collect them. And this is the proof of F in Robinson resolution. If you start here and you do a resolution down the proof, we get the propositional proof of F in Robinson resolution. We haven't assumed anything. The only assumption we still have in this proof is that SAT is in P, because that gives everything else. This is, of course, possible to do more formally. So we define the delta, and delta of F is the propositional Robinson resolution proof of F. Then, if we can prove F from axiom B in polynomial computing time, then we get this delta in polynomial computing time, and the delta is the name of this polynomial proof. Then, if we have 9, we get a formal propositional proof of F in Robinson resolution. If we have 11, then we can say safely that there exists a resolution proof of F for all tautologies on the DNF. That is what we can say here, right? Because we produced the proof. And then we can at least say that there exists a proof. But it remains to measure the size of it. And I've done that. Here I talk a little bit what can happen, why this size, as I'm saying here, the size of this resolution proof is only polynomial. And I gave the argument for the tree. It never grows more than polynomially in any direction. So the entire propositional proof is polynomial size. That's what we have. So we have that for all sufficiently large tautologies F on DNF, we have that exists a resolution proof of F in polynomial size, because we have actually constructed it. That was the delta. Okay, so for this result, the only thing we have assumed, and we haven't sneaked in any other hidden assumption, and Hilbert's proof theory is good at that, because it has rules for how you deal with assumptions. So we can transform this, if we want to a proof in Hilbert's proof theory and check that nothing has been sneaked in. So if we now discharge this assumption, then we have this result. That is, if SAT is in P, then for all sufficiently large tautologies, there exists a proof in Robinson resolution of f in polynomial size. That is what we have. And how did we get that? Well, we started with f and we run it and used the axiom as a logic program. And we let the program go on with polynomial many moves with the head. And then we measured the proof that we got from the axiom. And the proof of the tree, the propositional proof, is only the size of it is only polynomial size. So there exists one. That is what we have got. Okay, now we have this Hawkins result, and what he says, that it's not the case that all sufficiently large tautologies f on DNF have a Robinson resolution proof in polynomial size. That is what he says, and that is a well-known result. So this is essentially Hawkins' theorem that I have expressed in Hilbert's proof theory. Okay, now from this, if SAT is in P, then for all sufficiently large tautologies, there exists a proof in Robinson resolution of f in polynomial size. But Hawkins says that not all sufficiently large tautologies f on DNF have a Robinson resolution proof in polynomial size. Well, what's wrong with that? Because that's a contradiction. Well, what is wrong is that our assumption that SAT is in P can't be right. So that must be false. So we have our first theorem that says that SAT is not in P. Okay, but SAT is in NP. And there are two sets. So NP has a member that P doesn't have. So they can't be the same set. So we immediately get P is not equal to NP. Okay. Now then, any questions right now? Or do you want to come back with the questions after a break? Because it's just break time.